Okay, so we are in chapter 14 here, and last time we got into titrations after we talked about the buffers a little bit more. So remember, in a titration, you're adding usually a one solution to the next through a burette. Usually there's some type of unknown solution in that situation. And in a situation where maybe you don't know the molarity, maybe you don't know the molar mass of it, and you have a known solution. And when we do titrations, it is really nothing but consistently adding volume, obviously, from the burette. And because of that, what we typically have to do is an ice table in moles, very much like what we did with our buffers when we add something to our buffer. Um, we saw a titration curve for a strong acid, strong base titration. And in this titration, again, our strong base is up in the burette, and we're adding that to our strong acid in the beaker or the flask. And we saw a titration curve, looks something like this. And that is our pH. In this case, this is the volume of base we are adding. And remember that kind of when we look at a titration curve, there's really kind of four important sort of sections of the curve. The very first part here is before we start the titration. The second part is when you start the titration up to your equivalence point. The third part of the titration curve is the actual equivalence point. Remember that the equivalence point is the point in the titration where the moles of the acid will equal the moles of the base. So that is the exact point where they are equal to each other. And that is a third part of this titration curve. And then the part that, again, that you haven't probably typically done when you did a titration, but it is the part that comes sort of after the equivalence point. Thank you. And that obviously is when you're just, in this case, continuously adding base. Now, depending on where you are in the titration curve, you do have to do some calculations to figure out the pH. So in this type of titration, as we talked about initially, all you have in the flask or beaker is your strong acid. And because of that, it is a strong acid, which most likely means that you then have the H plus concentration. And really, at that point, you could just go right into your pH equation there to get the kind of opening pH of your solution when you're doing this titration. The second part of the titration curve, which is obviously when you start the titration, you do need to do an ice table. And remember that the ice table here does need to be in moles, but then you should convert to molarity at the end using the total volume. The purpose really of the ice table at this point is to figure out really how much of your strong acid you're going to have left over. Because at this point in the titration, the strong acid is like the excess reagent, and the base that you're adding is like the limiting reagent. So the base is going to get used up, and you will definitely still have some strong acid left over. And that's what you'll see in your ice table. You will have a strong acid left over once you get to the equilibrium line. You will also have a salt that's present, as we talked about, and that salt is going to be a neutral salt as it comes from a strong acid and a strong base, so you don't have to really worry about that. So at that point, once you do your ice table, you'll basically be able to figure out really the concentration of the H plus from that strong acid, and at that point, you could then go into your pH equation and get the pH. In this type of titration, once you reach the equivalence point, and as we talked about, we do typically see a very vertical sort of rise to the equivalence point, and then we typically will actually see a rise after the equivalence point as well. And as we talked about, that means, again, we're not adding a lot of volume, but we are seeing a lot of change in pH in that sort of range of the volume of the equivalence point. And again, that is why, as we talked about, when you do a titration, you just add one drop. It goes from like no color to like really dark pink because it doesn't take a lot of volume to change the pH a lot. And that changes your indicator color a lot because the pH changed a lot in that area. What you really need to do in this type of titration is not very much at the equivalence point, and that's because as we went through sort of that little mock table of what's going on at the equivalence point, what you will end up with at that point of the titration is really just a salt. So you'll just have a salt left over. And that salt, again, is going to be a neutral salt because, as we just mentioned, it comes from a strong acid and strong base. So the pH should be 7 in a titration of a strong acid and strong base at the equivalence point. Then if you continue on there past the equivalence point, you do need to do, again, an ice table here in moles. And like we talked about before, then convert it back to molarity using the total volume. The difference, though, at this point is because you are past the equivalence point, what ends up happening is your acid actually becomes the limiting reagent and your base is like the excess reagent because you just keep adding base right from the burette. Don't stop, basically. And what that happens in that case is it should be the acid should be your change in that table. And what you'll end up with is actually a strong base left over. You will also, again, in this case, still have the salt that's neutral you don't have to worry about. But because that is a strong base, remember that that will get you your OH minus concentration, which then would probably get you your POH and then to your pH at that point. And again, we do need the ice table basically to figure out how much of the strong base is left over at that point. You can also, as we talked about, always sort of use your ice table, especially when you get to the equilibrium line to kind of see what's going on, what's left over, kind of point you in the right direction. Remember, when we do these ice tables, typically with moles, we actually don't use X's because we know what the change should be in that case. And we actually use numbers most of the time. Any questions on any of that we talked about last time there? All right, so that was one specific type of titration. Let's talk about another titration that we'll talk about here. And that is not it. Maybe that is it. There we go. So let's talk about a titration of a weak acid and a strong base. So this is a titration that you did before. You did it perhaps in 200A. Let's see, if we take a little bit of acetic acid here, which is a weak acid, and we titrate it with some sodium hydroxide, we are going to get a double displacement reaction, and we will get some sodium acetate and some water in this case, right? So that is the reaction going on. Again, in terms of orientation here, we're going to have up in our burette our strong base or our sodium hydroxide. Down in the beaker or the flask is going to be your acetic acid in this titration. So once again, here we are adding base to our acid. And we see a titration curve that's very similar to what we see or saw there in our strong acid, strong base. Again, this sort of S curve. You'll sometimes notice that the pH, though, the initial pH will start a little bit higher because it's a weak acid versus, say, a strong acid in some cases. But we have that traditional sort of S curve. There is still really the same 4 spots we're going to talk about. Again, spot number 1 is really before you start the titration. Spot number 2, again, is once you start the titration up to your equivalence point. Spot 3 there is going to be your equivalence point, and past your equivalence point is going to be really the 4th part of this titration curve. So much like we did with the strong acid, we're going to go through each of these points and again sort of identify what is going on so you understand how to kind of work through these problems. So let's just start with part number 1 here, which is really before you start the titration. And obviously at this point, before you start the titration, the only thing you have in that beaker is, in this example, acetic acid, but you basically only have your weak acid in your beaker or your flask in this case. So if we need the pH of a weak acid, we will have to do pretty much a Ka problem, right? So that is going to involve really an ice table. And it's just going to be like we did in the previous chapter, this weak acid dissociating into, in this case, acetate and H plus. We would do an initial concentration here. Because we have not started the titration at this point, we have not mixed any volumes or anything like that. So we could use the initial molarity in this table, and this will be just a regular 0, 0, minus X plus X plus X. At equilibrium, obviously, molarity minus X, X, and X. This would go into your Ka expression. You would solve for X in this case, like normal. Again, either assumption, quadratic, whatever it may be. When you do that, X will equal the H plus concentration, as we could see from our table here. And that would then allow you, obviously, to go into your pH equation. So as you can see here, this titration a little different than the previous one. Got a little bit more work there up front because we're dealing with a weak acid versus a strong acid in this particular case. So you can, again, just do a basic sort of Ka weak acid problem. Questions on that there? All right, so we get our initial pH this way, and now we're ready to sort of start our titration. So in this case, when we start our titration, we will need obviously a reaction to occur between our acid and our base, which is what we have written up there on top. So let's take a look at what happens in sort of that second region. So once we start the titration, and this would be obviously before the equivalence point in this case. And again, we will get that reaction. So we'll do our acetic acid in this case. We will do our sodium hydroxide. We'll do a little double displacement reaction here, a little sodium acetate, and some water in this case. Now, at this point, since we are adding sodium hydroxide to it, it is definitely a situation where we need to do this table in moles, right? So this table does need to be done in moles. And again, we are starting with this one, and we are adding this one. And initially, once again, just like on the last one, I'm just going to make up some numbers here. So I'm going to say we started with 4 moles of acetic acid. So as we talked about last time, if we are before the equivalence point, whatever we are adding in terms of moles should then be less than what we started with, right? Because at the equivalence point, they're equal. So when we start, we're kind of rising to that equal, right, to hit the equivalence point. And then when we're past the equivalence point, whatever we're adding will then be more. So in this case, I'm just going to make up the number of 2. And this would be 0. Once again, in this type of ice table, yeah. It is because, again, when you look at molarity, right, which is the moles of solute over liters of solution, right? So as you continue to add volume and stuff like that, this number will be constantly changing, right? And that means that your molarity will be constantly changing every time you sort of add. What really doesn't change is the moles of the solute. And that really is when you take, for example, or talking about sort of like our acetic acid, which is down here. It really is the moles of acetic acid you have floating around in there that's going to react really with the moles of sodium hydroxide when that comes in there. And that's essentially the reaction. Really, there is between that and the hydroxide that's coming in. But those are really what you have available to you to actually do the reaction. The liters part of it is just, all the other stuff in there, the water and stuff that's really not reacting per se. So it's really those moles. And that's why the moles are consistent. So whatever molarity you start with, for example, in your beaker, you only have a certain amount of moles to react with, basically. And that's the important part, and that doesn't change. And unless obviously you add something to it to react with it, and that's why we do it in moles, because molarity will constantly be changing.
So for these type problems, do we add our own values for like base or acid, or are we given specific values like?
Yeah, no, you would be given, obviously, we haven't done an example, but like the example we did yesterday, you would be given, like, for example, the molarity of the acid and the base and the volume that you added at that point. And from that, obviously, you could use, right, liters times molarity, right? And that will get you to your moles and stuff like that. So you'll be given those things. The only time you may not be given is like we talked about when you reach the equivalence point. Sometimes in problems, they'll just say, what is the pH at the equivalence point? And they may not tell you how much volume you need to sort of add to get there. So that is something additionally that you might have to calculate along the way. But yeah, you'll actually have numbers, obviously, to get to those numbers. Other questions? All right, so and again here we want to do our moles, and at this point we definitely have more moles of our acid we started with than our base that we're adding. And this is also a good idea to sort of think about instead of just kind of going on autopilot and kind of going through the problem. And what I mean by that is to sort of have an idea as to where you are in the titration curve. I can oftentimes help you understand what calculation you should do, before you get too far into it and maybe get lost along the way. So again, it's always sometimes good to know sort of where you're at, so you can know what type of titration or what type of calculation you should do. Remember that it's always needs to be the smallest number, and I say that a lot because there will be a time where you will choose the larger number and get lost, and your brain just tells you I should choose the larger number. So don't do that. It should always be the smallest number. So in this case, the change is going to be the sodium hydroxide that we're adding, which would be -2 moles, -2 moles, and +2 moles. That means when we reach equilibrium, we will have 2 moles of this one, 0, and 2 moles of this one. So as we talked about last time, at this point, it really is good practice to convert your sort of moles back into molarity. Um, and again, we would convert it back into molarity using the total volume, which should be really the volume of the acid plus the volume of the base that you added at that point. Obviously convert it into liters. So you would convert these guys sort of back into molarity, again, using our total volume at this point. If you are, again, not sure sort of what you should do next, once again, the ice table can really be helpful for you, because if we look at the ice table, we have basically this guy left over, and we basically have this one left over. And hopefully you could recognize that these two things are actually related to each other. That's acetic acid, which is a weak acid. That is sodium acetate, which is a salt of its conjugate base. That is barely a buffer at this point. And you will always hit a buffer at this point of the titration in this type of titration. So this is what we were kind of talking about the other day when we were talking about that you can actually make a buffer as a result of the reaction of a weak acid and a strong base. And this is an example of that. The buffer is not the strong base part. It is actually what you end up with at the end of that reaction is actually generating a buffer in this case. So in the part as you start the titration before the equivalence point, you will actually always hit a buffer. And what that means is at this point to get to the pH, probably your best bet would be the Henderson-Hasselbalch equation, right? Which is the equation that we want to use for a buffer. You could also, if you wanted to avoid the Henderson-Hasselbalch and still do an ice table, again, a reminder at this point, because you just made a buffer, the ice table, important part, if you choose to kind of take that approach, would be just a Ka type of problem. But the important part of that ice table would be you should have the molarity of this guy 0. And once again, you do have the molarity of that guy is coming really from above. And obviously you would use your concentrations from above. The rest of the table would be just like a normal sort of ice table. You would obviously go into your Ka, solve for X. That would equal your H plus, and then you could go into your pH. Or again, you could just go into here and not do that at all, and which might be, again, maybe a quicker move if you could recognize it. So again, this type of titration, a little bit different than the strong acid, strong base titration when we are before the equivalence point. Here, before the equivalence point, you're always going to hit a buffer. And that is also why, for example, if you sort of look at the curve, it kind of is able to withstand a little bit of the pH. This is also what happens and why you see that jump as you go through here to the equivalence point, because as we talked about, you make a buffer as you're going through this, and then you kind of blow through your buffer because all you're doing is continuously adding base, right? So if you remember, as we talked about with the buffer, as you add that base, your acid part of your buffer is going to get less, 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 less. And at some point in titration, you're just continuously adding the base. So eventually the acid part is going to go away. You're going to now influx a lot of OH minus really, really quickly into that solution. That's going to cause the pH, right, to kind of skyrocket really quick. Even with like a drop or so, it will jump really, really high because you basically just blew through your buffer. That's also why sometimes people are surprised when they do that titration, like you maybe did in 200A. It's going along nice and stuff. Doesn't look like it's changing all that much, but just out of nowhere, it just seems like it jumps, right? And that's basically what's happening. You have that kind of buffering area as you're doing the beginning part of that titration, then you blow through it and you get a big jump in that OH minus. Any questions on that there? So really spot number 2 here is a buffer sort of situation that's going to occur. You really need kind of the first ice table to figure out what is really your molarity or your molarity of your buffer components. And then again, you could use the Henderson-Hasselbalch. So let's talk then what happens as we do reach the equivalence point in this type of titration. So once we reach the equivalence point here, in this type of titration, we are still having obviously our reaction between our acid and our base. And again, we are starting with this one and we are adding this one. And again, we're going to do this in moles because clearly we are titrating at this point. So once again, just making up the numbers here for our example, I'm going to again assume that I am at 4 moles of my acetic acid. And because I understand the definition of equivalence point is the moles of the acid should equal the moles of the base at this point, I know automatically I should have 4 moles of sodium hydroxide at this point if I'm at the equivalence point. Again, as we talked about last time, you may not be given the volume to reach the equivalence point. So again, you might have to figure that out. If it is a one-to-one relationship, you can use M1V1 equals M2V2. You also, as I mentioned last time, because you know that this guy should equal this guy, you know really the moles of the base that you should have at this point, and you most likely would know the molarity here of your base. So you will know the moles, you'll know the molarity. So you could just actually just use as well the molarity sort of formula to figure out the volume of sodium hydroxide needed. Once again, the reason you will need that is obviously at the end of this table, we got to convert back to molarity. So you would need to know the volume of base you added. And that is a common error when people come across a problem like that. They only use the one volume that's given to them which in this case would be like the volume of the acetic acid, and don't ever figure out the volume of the sodium hydroxide. So now you're going to be converting to molarity with the wrong volume, and your answer is going to be wrong. So you got to be careful on that. At this point here, we obviously would have 0. The good news, as we talked about there, is you cannot really choose the wrong number here since they're both the same. So we're going to go with -4 moles, -4 moles, and +4 moles. That is going to give you 0, 0, and 4 moles. Once again here, we're going to divide by the total volume and convert that back to molarity. As I mentioned before, that is probably really the best move because in most cases you do need a molarity. Once again, as we talked about last time in the previous step where we hit a buffer, technically speaking, you could go into the Henderson-Hasselbalch with moles and it'll be okay. But if you are going to go into the ice table, you do need to put it into molarity in that last step as well. So, but if you put in the molarity, you're always sort of in the right units. At this point, if you're not sure what is going on, we could again use the ice table to kind of help us out to see what's we have left. And clearly at this point here, we have a salt left over at this point. That salt is sodium acetate, which is basically a sodium ion and an acetate ion. And we want to figure out really, the pH, right, of this solution at this point. So hopefully you could recognize that this is a salt. And when we have a salt, we always want to think about, will it go through hydrolysis, right? And we know that this sodium part should not go through hydrolysis because it comes really from sodium hydroxide, or it's group 1 on the periodic table. What about the acetate? Will it go through hydrolysis? The answer, right, is yes, because it comes from acetic acid, which is a weak acid. So this guy right here will go through hydrolysis. And he's got some water right there to react with no problem, right? So what you have at this point in the titration is you will actually have a second reaction that's going to occur that's going to affect the pH. You will actually have a hydrolysis reaction of the acetate reacting with the water in this case. And again, if you're not sure how it's going to react, obviously this is a weak acid, which means this would technically be its conjugate base, and it's going to react as a base in this case. Bronsted-Lowry definition of base is it's going to accept the H plus over there. The result of that is you will get back your acetic acid that it came from, and it will produce hydroxide, right? So when we look at this hydrolysis reaction, we should know right off the bat this solution should be acidic, basic, or neutral. This one should be. This one should be basic, yeah, because we are forming that. So we will use our equilibrium concentration of our salt from the first table as our initial molarity on the second ice table. And this ice table should be done in molarity, which again is why it's really good to convert back to molarity after the first ice table. You really don't want to roll in here with moles because you will get the wrong answer if you don't adjust it correctly at the end, and most people probably won't. So just roll in with molarity at this point and you should be good. This is going to be a 0, 0. And really, since we're using molarity here, we'll go back to X's at this point. And we will end up with the molarity minus X, X, and X. This would go into our K expression, right? Which in this case is our products over our reactants. By the way, this is a K, A, B, C, D, F, G. This should be a K, K, B, yeah. Also because of that. In this problem, will you have the Kb? Probably not. You will probably have the Ka value for the weak acid in this case. So this would be another situation, much like hydrolysis problems, where you got to have the Ka times the Kb equals the Kw. So you most likely will have to do that. You will solve for X here. Also important to remember and write these equations correctly. The X is the hydroxide concentration, not the H plus concentration. So that is the hydroxide concentration, which means a little POH and then to your pH. So you can see in this type of titration, much different than the first one where you just write a pH of 7. Happy days on that one. Here you have to do really 2 ice tables in order to get yourself to the pH. The first ice table here really is just to figure out what is the concentration of your salt at that point. The second one is a hydrolysis problem like we did previously to figure out the actual pH using obviously the concentration from the first one. Any questions on that there? Yeah.
The initial ice table, did you mean the very first one?
No, I mean the equilibrium. So that's where we're at, right? So really we're in all this, right? We're looking for like when you open the burette, right, and you add something in it, at some point the reaction is going to kind of finish, if you will, and it's going to reach equilibrium, right, at that point. And that's what you're looking for the pH at that point, right? So if you remember, well, you probably didn't use a pH meter, but you will this week, next week, use a pH meter. But when you open and you shut it, you wait kind of for the pH to settle and that's what you're looking for. So it's the equilibrium concentration. So the purpose of the first table is really to get that equilibrium concentration so that you can essentially use it in the next step in the next table that she has to do at this point. Other questions? All right, so that is what's happening as we reach the equivalence point here. So as we talked about, we have that jump to the equivalence point as we blow through that buffer. At that point, you're really just adding sodium hydroxide, and a lot of OH minus is really just dropping in there. And again, that's why we continuously see the pH rise. Sometimes when you're doing a titration curve like you'll do next week, some people miss the actual equivalence point because it just keeps going, right? And they wait on their pH meter for it to stabilize, and it never does because it just keeps going straight vertically up, and your pH just keeps rising and rising at that point. All right, so let's talk about what happens after we hit the equivalence point. Again, your indicator didn't stop you and you decided, let's just keep going. So after the equivalence point in this case. So in this type of titration, we're still dealing obviously with the same reaction. And that is our acetic acid and our sodium hydroxide here. Giving us our sodium acetate and our water. So again, starting with this one, adding this one. So once again, as we've been doing, we're going to use moles, obviously, in this table because we're adding volume. Here initially, just using our made-up number of 4. As we talked about last time and today as well, again, if I am past the equivalence point, then whatever I'm adding should actually be more moles than I started with, right? Because they are equal at the equivalence point. So if you keep adding, obviously you are past that. So again, just making up the number going to be 6 in this case and 0. At this point, just like in the previous titration, we do get sort of a switch that occurs in terms of what's our limiting reagent, what's our excess reagent. Our acid that we started with actually now becomes our limiting reagent. Our sodium hydroxide in this example is our excess reagent. We have plenty of it because we just keep adding. That means that the change here is actually going to be the acid in this case. And that's going to give us a -4, -4, +4 moles. That means at equilibrium 0, we'll have 2 moles of this one and 4 moles of this one. Once again here, like normal, we're going to convert back into molarity using the total volume. And again, at this point, you could kind of use your ice table to help you maybe try to figure out what is going on. And we do have 2 things that are left over at this point. Are those things a buffer? They are not a buffer. Yeah, they are not related to each other in a buffer sense. And really, you should not use the Henderson-Hasselbalch equation here, which again is a super common error people make when they end up with two numbers at the end of the ice table. They just figure into that equation. It seems like a good idea. It's a bad idea, by the way. Yeah. So we really have two things at this point left over. We got our salt that we just talked about, and we also have this guy, which is our strong base. Now, clearly, as we just saw at the equivalence point, our salt will go through hydrolysis and it will act as a base. When it does that, it will accept the H plus right from our water as it came from acetic acid. And we basically at this point have two bases. So we do have the salt that will go through hydrolysis. It will produce hydroxide like we saw at the equivalence point. But we also have a strong base that is present at this point. And between really these two bases, clearly the strong base is stronger. And the strong base is really going to be the one at this point in the titration that's going to be the major contributor to the pH because, frankly, all it needs to do is have you drop it in, and boom, we're going to have hydroxide basically be produced in that solution by it going for a swim. So at this point in the titration, even though we do obviously have that salt doing some reaction, its contribution is going to be negligible. And really, the important part here is going to be really the concentration of your strong base, as that's going to be the major contributor of OH minus to the solution. So because that is a strong base, that means that the molarity that you got here is going to be the hydroxide concentration. Again, not the H plus concentration. That means that you can calculate the POH and then get yourself really to the pH at this point. So at this point in the titration, we really need this table to figure out what is the concentration really of the strong base that we have added to the solution at this point, so that we can then calculate the pH really based off of that, as that will be the major contributor at this point. Any questions on that part of it there? So obviously, as you can see, and based on what we've talked about here, this type of titration is really a much different type of titration in terms of the calculations that you would do than say our strong acid, strong base titration. So it is really important to know what type of titration you are dealing with so you can understand really what type of calculations you should be doing. But these four parts here are really four calculations that we have done previously. The key is to make sure you know which calculation you should be doing. So once again, here at the very beginning, we have just a weak acid, which is really just a Ka type calculation, right? Over here, we're going to end up in a buffer type calculation. Here, we're going to end up in a hydrolysis calculation. And here, we're going to end up in a strong base calculation. So this really is what I was talking about earlier, that if you understand from the very beginning, for example, where you are in the titration curve, you should know, hey, I should be doing like a buffer calculation at some point, or maybe I should be doing like a hydrolysis calculation before you even get into it. And again, as I mentioned before, sometimes that's much easier to know what you should be doing, right, than trying to figure it out as you're going through it. Any questions on that there? So why don't we try one here? Why don't we do what is the pH of a solution after, we'll go with 21 milliliters of 0.1 molar acetic acid. I'm sorry, 0.1 molar sodium hydroxide is added to 25 milliliters of 0.1 molar acetic acid in a titration. All right, the Ka for acetic acid, 1.8 times 10 to the minus 5. All right, let's take a few moments there and calculate. Take a look here and see. So clearly we're doing titration, and obviously we're doing the same titration we've been talking about. So again, for orientation purposes here, we have our sodium hydroxide up in the burette. And again, we have our acetic acid there in the bottom beaker. So clearly we are going to have a reaction. Clearly we've started adding some sodium hydroxide here. So we definitely are going to need to do our ice table in moles. So might as well just start with getting the moles of everybody there. So our moles here of sodium hydroxide, once again, we do need to convert our volume into liters. Otherwise, you will have millimoles, which is different than moles, by the way. So 0.021 liters times our molarity of our sodium hydroxide, which is 0.1 moles per liter. Again, here the liters are going to cancel when we multiply. We'll take 0.021 times 0.1, and that's going to get us here 0.0021 moles of sodium hydroxide we are starting with. Over here, we'll do our moles of our acetic acid. Also going to convert our volume here into to liters, divide by 1,000, or move your decimal place one place to the right, 3 places to the left, or one place to the right if you want to do it wrong. So we're going to multiply it there by its molarity. There we go, and our liters are going to cancel, and that'll get us our 2.5 version of that basically. 0.0025 moles of acetic acid. So now that we have our moles, which we know we're going to need in our calculation here, we're going to set up our ice table, which we do know that we need. So we got our acetic acid, we have our sodium hydroxide here. And again, going to give us some sodium acetate on our double displacement reaction and some water. We are initially starting with 0.0025 moles. And again, this is what we're starting with. This is what we are adding. And here we have 0.0021 moles and 0. So once again, as I mentioned earlier, it's good to know sort of where you are in the titration curve, right? So you have an idea really as to what you should be doing in your calculation. Again, you can definitely figure out where you are in the titration by really just the initial line in your moles, basically, right? So again, on comparison of what we started with moles to what we're adding, we could see that what we are adding is less than what we started with. And because it's less than what we started with, we know we are definitely before the equivalence point in this case because of that. That also should give you a pretty good hint as to what we should end up with and what calculation we should do. So let's see if that is the case here. So because we're before the equivalence point, the sodium hydroxide that we're adding is going to be the limiting reagent and get used up here. So we're going to go with that as our change. And again, remember, it should always be the smallest number there, so you do not get any negative type numbers. That is going to get us here at equilibrium. We will end up with 0.0025 minus 0.0021. 0.0004 moles. That's going to be 0 and 0.00210 moles. Again, at this point, as I mentioned previously, we do want to convert back to molarity, but before that, any questions so far on the ice table? All right, so to convert back to molarity, obviously we need to take the volume we started with and the volume that was added. So clearly here we had 25 and 21. I'm going to try it without the calculator. 46 milliliters, I think, is what we end up with. So we're going to divide this. Once again, we do need to divide it by the liters version of that. So 0.046 liters. And that's gonna hit me some molarities there. So we'll do that guy there. Looks like 0.00869. Yeah, I'll go one more so not sort of rewrite it. I'm missing the six there. 0.00210 divided by 0.0460. Looks like 0.04565 at this point. Again, if we are not sure, what is going on, or maybe you didn't figure out where you are in the titration curve, you should be able to hopefully look and see what you got left in your ice table, which are these two things. And once again, this should also validate if you did figure out where you were, that is a buffer, right? So, and that is what we would expect to hit at this point, as we have a weak acid and its conjugate base left. So we do have a buffer. And again, probably the safe move would be the Henderson-Hasselbalch equation. So again, you could also do the ice table, a second one. I am personally going to do the Henderson-Hasselbalch here because, seems much easier perhaps. We are going to need the pKa value that we could get from the Ka value that was given to us. So the pKa equals minus the log of 1.8 times 10 to the minus 5. That's a 4.74. And that means that we are going to go in here 4.74 plus the log of our base. Remember that our base has one less hydrogen and typically a spectator ion, like a sodium here in this case. So obviously the other guy is acetic acid, so that would be our acid. 0.04565, 0.008696. And let's see here how bad I did. 0.00869. A little log action plus 4.74 is like a 5.46 pH at this point. Any questions on that there? You see how we did. I think this was the titration they did here. So 21 would be between those numbers. So 5.46 or whatever we got is more than 5.38, less than 5.61. So that's good. I'll fit in there. Any questions on this type of titration? So again, you can see it is different than a strong acid, strong base titration in terms of what's going on and how you calculate it. The key with titrations is, again, you actually do know how to do all these calculations, but the key is people have a really hard time with which one they should do. Yeah. And so a lot of people just default to, I got two numbers, I'm just going to keep throwing it into the Henderson-Hasselbalch and hope I get lucky, right? So again, understanding where you are in the titration curve, understanding what type of calculation you should be doing is really, really helpful as you kind of go through these. Any questions on that type there? All right, so the next type of titration, I know like there's this many different types of titrations there are. So the next type of titration we're going to do is actually a strong acid titration with a weak base, or a strong acid titration to a weak base. The orientation of this is a little bit different than you may think. So we'll take like a weak base like ammonia, and we're going to add a strong acid to it like hydrochloric acid. And when that occurs, we will get, in this case, ammonium chloride as it comes together. So the orientation of how this titration is happening, actually up in the burette, is the HCl. So we're actually adding the acid to the base in this case. So down in the beaker is your ammonia. So once again, we are adding the acid to the base. That is also why when we look at our titration curve here, it's upside down. Yeah, and it's upside down because we are actually starting with a base and we're adding acid. So the pH is actually coming down, right? It's kind of the same curve, but kind of going in the opposite direction, starting high, ending low here when you do this type of titration. Even though it's sort of upside down, there's still really the same four spots that we've been talking about in the last two types of titrations. We still have the very first one, which is obviously before we start. We have the second spot, which is as soon as we start the titration to the equivalence point. We have the third spot there, which is the equivalence point. And much like the other ones there, we have actually after the equivalence point there and sort of our fourth spot. So once again, we're going to go through each of these spots and hopefully understand what's happening in each of these spots. So again, you'll understand what type of sort of calculation you should do. So starting with the very first case here, before we start the titration, and again here, before we start this titration, in this particular case, the only thing you got kind of in your beaker is your weak base. And because it's a weak base, to get the pH of it, we do have a little bit more work. It is similar to what we do in the last titration. It is not a Ka problem, but it is going to be really just a basic Kb type problem in this case. You will have your weak base that obviously will react with water. And it will act as a base, which means it will accept the H plus over there. And when it does so, it will make NH4 plus, and it will make hydroxide, which again is why it's a base. By the way, you could also, keep ammonium and hydroxide together as ammonium hydroxide, but I'm going to keep it separated in this case. This would be a regular sort of Kb type problem. Again, because you have not started the titration, you have not added any volume, so you could just use the molarity of the base in this case. These guys would be zeros. We would do a minus X, really plus X, plus X. That means at equilibrium, molarity minus X, X, and X. This would go into your Kb expression. Obviously, here you would solve for X, assumption quadratic, whatever it may be. The X, again, you do have to remember in this case, since this is a base, is not the H plus concentration. So once again here, this is the OH minus concentration. And again, why it's important to be able to write that equation correctly. Can't tell you how many people I've seen write that equation with H3O plus on the right-hand side. Yeah, so again, that's going to send you down a bad path. This is going to get you POH, right? And then to your pH. So again, a little bit more work than we saw with the strong acid, similar to what we see with the weak acid, except as a weak base problem. And that will get you to your pH at the beginning. Any questions on that there? Now, number two, once we start the titration here, and again, before the equivalence point, we obviously are going to get a reaction. So again, here before the equivalence point, we're going to get a reaction between our ammonia and our HCl. And in this case, it is going to accept the H plus over here. And you will get ammonium and you will get chloride. You could, again, if you wanted to, in this particular example, you could keep them together as ammonium chloride. I'm going to separate them for reasons will become clear shortly, but you could absolutely just keep it together if you wanted to on the right-hand side. So when I look at this, obviously, because we are adding volume, we started our titrations, we are back to moles that we need. And that means initially here, I'm just going to make up numbers like I did before. I can go with 4 moles, and this is what we are starting with in this case, and this is what we are adding. And again, because I'm before the equivalence point, just like previously, we know that the moles should be less than what we started with because they're not equal yet. And again, making up the number of 2 in this case and 0. Once again, at this point, what we're adding is the limiting reagent because we have not reached the equivalence point. So the change is going to be that one. And plus 2 moles. And here at equilibrium, we will end up with 2 moles of this guy, 0 of this guy, and 2 moles of this guy. I separated out chloride over here and I ignored it because what's the deal with chloride? It is neutral, right? Not going to affect the pH. So once again, maybe no need to kind of throw some numbers in there that you might want to use incorrectly later. So again, obviously, if you kept together, you would just have one thing on that side and hopefully understand that the chloride obviously is not doing too much there. It's really just a spectator ion in this case. Like normal, we're going to convert this back into molarity at the end of this first ice table. Just really good practice to kind of do that. And if you're not sure what you have going on at this point, you can again look at the ice table and see what you have left over at equilibrium. And we really have these two things left over at equilibrium, which is ammonia and ammonium. And these two things, hopefully you recognize, are related to each other by one H plus, and that's a weak base and its conjugate acid. That again is now going to be a buffer. So this is an example of actually creating a buffer as a result of a reaction of a weak base and a strong acid. Again, the buffer is not the strong acid part. It is actually what you get once that reaction is over. You're left with a buffer. So much like in the last titration, before the equivalence point, you are again going to be creating a buffer. The only difference is you're going to be creating really a basic buffer for most of it. So you're going to get a basic buffer rather than an acidic buffer, but it's still a buffer. And because that is still a buffer, that means we could go into our Henderson-Hasselbalch equation, and we can obviously get our pH that way. You could also still do an ice table if you choose instead of the Henderson-Hasselbalch. If you did the ice table, you actually have two options in this particular case. You could do a KB ice table with the NH3. And again, you would get the OH minus if you kind of did that. You could also do a Ka one with the NH4 plus and use the Ka value for NH4 plus. So you actually have two options if you want to kind of go that route. They both routes should get you the same answer. Any questions on that there? So this one kind of similar to the last time. You are going to hit a buffer in this region. You got like a KB happening there at the beginning. Now we get ourselves to the equivalence point here. And at the equivalence point, we will have our moles of acid equals our moles of base. So once again, obviously, we will have a reaction, NH3 plus our HCl, making our NH4 plus and Cl minus. And again, we are starting with this guy. We are adding this one here. So initially here, we'll go with our 4 moles. Once again, we should know we should have equal moles at this point because we're at the equivalence point. So 4 moles and 0. Again, I'm going to ignore the chloride as it's not important. We're going to go -4, -4, and +4 in this case. That means at equilibrium, none of that and none of that, which is what should happen because they both should be used up. We will have 4 moles of this guy. Once again, here converting into molarity using our total volume like we did before. And we can see here again, we really do have a salt left over. And if you kept it together, you have the ammonium chloride, which is really the salt that's left over at that point. We sort of already at the beginning eliminated any problem for chloride in terms of the salt doing anything. But again, when we look at the NH4 plus, that does come from NH3, which is a weak base. So that is a weak base. That would mean that this would be technically his conjugate acid. And because it comes from the weak base, this salt will go through hydrolysis. So much like we saw in the previous one, we will need a second ice table at this point. And again, it's going to be a hydrolysis reaction. So you will take your salt part that will go through hydrolysis. And again, if you're not sure how that's going to react because it comes from a base, it will react as an acid, which means in this case, it's actually going to send the H plus over to the water. The result of that is you will get where it came from, NH3. And when that water accepts the H plus, you will produce H3O plus in this case. And once again, without doing the calculation, because we are producing H3O plus, we should know we should hit an acidic pH at this point. And where we get our initial concentration is really the equilibrium concentration from the previous table. Again, that's the purpose of the first table, is to get that initial concentration that comes into here. At this point, these will be some zeros and x's. And really here, this is going to go into our Ka. Again, we are going to need a Ka because we have H3O plus in this case. Once again, very similar to probably what you would have in the previous titration curve. In the actual problem, you may be given just the Kb value for NH3. So again, common error, people just use that value at this point and get the wrong answer. So here again, you got to watch out for that. You do need the Ka value. You're probably going to again have to use Kw to kind of switch it around. Once you get that Ka value, you will solve for x. The good news on this one is X actually is the H plus concentration in this case. So that will equal your H plus, and that would then get you right into the pH. So again, very similar to the previous titration, it does require two ice tables. The purpose of the first ice table is to get that salt concentration, so you could do the hydrolysis problem. And then once you do the hydrolysis problem, you will do a second ice table there, which is the hydrolysis, and get your pH from it. So again, much like the last one, we got a little hydrolysis happening here at the equivalence point. Any questions on that there? All right, then that brings us to the last part of this titration curve, which is number 4 here, which is after the equivalence point. And after the equivalence point, we got excess amount of acid being added. You just keep adding your acid basically in this case. So again, we will have our reaction. Again, we're going to do it in moles, and we're starting with this guy. We are adding this one here. So I'm using my made up number of 4 moles. Here we are past the equivalence point. So again, what we're adding is going to be more moles than what we started with. So we'll go with 6 moles here and 0. Change is going to be the switch that occurs in this case. Now the base is the limiting reagent. So that's going to be minus 4 moles, and plus 4 moles at this point. That means at equilibrium, 0, 2 moles, and 4 moles. Again, converting back into molarity at this point using our total volume. Here we could see, just looking at our ice table, we have 2 things left over, 3 things if you look at this guy, but really we don't have to worry about that, guys. We've been talking about. Again, this is not a buffer at this point, right? Because these things are not related to each other as a buffer. We actually here have this salt that will go through hydrolysis like we saw at the equivalence point and act as an acid. And we also have this one, which is a strong acid. So once again, really at this point, you kind of have like 2 acids left over. And very similar to the previous titration, in this case, that sort of NH4 plus has to go through hydrolysis. It is not going to be the major contributor really to the H plus. It is going to be as you're sitting there opening your burette and dumping it, your HCl into that solution, it's just going to break apart into H plus, all that H plus coming from the HCl that you're adding. So again, we ignore the contribution of the salt at this point in this titration, much like we did in the previous one, and we go with our strong acid. And because that is a strong acid, that is going to give you your H plus concentration, and then you will have your pH at that point. So again, the purpose of the ice table here at this point in this titration is to, again, really figure out how much of the strong acid you just dumped in there past your equivalence point. And again, because it's just going to completely break apart at that point, that is going to be the major contributor basically to H plus in that solution, and that will give you your pH. So it's a sort of strong acid type of problem at that point. So as you can see, this one is upside down, if you will, but it actually is the same for sort of types of calculations that you end up with that we saw in the previous titration. Again, the key is to understand where you're at so you can do it. Also, when we think about the three titrations that we sort of talked about, if you're our strong acid, strong base titration, your equivalence point should be 7. If you're a weak acid, strong base titration, your equivalence point should be basic, which is, by the way, why we use phenolphthalein that works in the basic pH range when you do that. And if you're doing this type of titration between a strong acid and a weak base, your equivalence point should be acidic. So you would want to choose an indicator, obviously, that's acidic that would work well in that range. So those are things that you want to kind of think about as you're doing titrations, where your equivalence point should be. You should actually have a pretty good idea. Should it be acidic, basic, or neutral, depending on the type of titration you're doing. Any questions on that there? So why don't we try one here? Why don't we try, let's do this. What is the pH after after 27 milliliters of 0.1 molar HCl is added to 25 milliliters of 0.1 molar ammonia. The Kb for ammonia, 1.8 times 10 to the minus 5. All right, give it a go, see what you come up with. Okay, let's take a look and see how we're doing. So we want to know what is the pH of this titration we've been talking about. Again, in this case, we do have the acid up in the burette. We are adding it to our base. So we are going to have to do an ice table because clearly we've added. So we're going to get our moles of everybody. So our moles of HCl here would be 0.027 liters times the molarity, 0.1 moles per liter. And that's going to get us here 0.027 times 0.1, 0.00270 moles of HCl. We'll also do that for our NH3. We have 0.025 liters times our molarity here of 0.1 moles per liter. So 0.025 times 0.1, 0.0025 moles of NH3. Again, we're going to need an ice table. So our reaction NH3 plus HCl, giving us NH4 plus Cl minus. Again, initially here, this is what we are starting with. This is what we are adding. So we got 0.0025 moles, 0.00270 moles, and 0. By comparing our initial moles of each of these, we actually do see that what we are adding is more moles than what we started with. That would tell us that we are definitely after the equivalence point in this type of titration. With that being said, we know that what should happen at this point then is actually our base in this case will be our limiting reagent and get used up. And that will be our change in this case. And That means at equilibrium, we will end up with 0 of that, 0.0027 minus 0.0025, 0.0002, and over here 0.00250 moles. Once again, I'm not going to worry too much about the chloride. Our total volume at this point, I got it lined up nicely. I'll just do it that way there. That's going to be 52 milliliters, I believe. And that means that is what we're going to divide this, guys, by 0.052 liters. Again, we do need to convert it into liters in this case. And that's going to get us here 0.003846 and 0.0025 by 0.052. 0.04807 molar. Once again, if we look at what we got left over at this point, it is HCl and NH4 plus. We are after the equivalence points, so we know this is not a buffer. We also know that we don't have to worry about the salt's contribution at this point, and that leaves us really just our strong acid. So once again, understanding where you are should lead you to this being the strong acid is the important thing. Because that's strong acid, that actually is the H plus concentration. That means the pH here minus the log of the H plus minus the log of 0.003846 in this case, minus the log of that there. And that's going to get us a 2.41 pH in this case, which is acidic. And again, should make sense since we're basically just dumping acid in at this point. And we can see how we did since this is this titration here. What did I do? 27. So that is between those two numbers. So that's pretty good in this case. Question on this type of titration. Okay, we're going to continue on here, wrap up this chapter, I think. Any questions so far on what we've been talking about, the different titrations? So again, we have 3 different titration curves that you do need to be aware of and be able to calculate, obviously, the pH anywhere along those curves. Any questions on anything? All right, so what we have left here, I think, is just a big old example here. So we're going to go through this example. Actually, you will work on it first, and then we'll go through it. So take some time. If you want to work together, you can on these different parts. And then we'll go through and make sure everybody's on the same page in terms of the answer. A reminder that if you come across a problem like this, where you're asked different parts along the titration curve to calculate, you should think of it as each part being like a separate sort of calculation, not that you're continuing on with the volume or anything like that. So first part, for example, here, we haven't started. Second part, we're adding 80 milliliters. The third part here, we're starting at 0, going to the equivalence point, what the pH is. For the fourth part here, we're starting at 0 and going 105 milliliters. So most of the time in books and problems like this, where there's multiple parts, you're asked about the same titration, you should think of it as always kind of starting at 0 and then kind of opening it up and stopping exactly at those points. All right, so take some time here, get the pH of each of those, and we will go through it together. For a pretty good dent into this example. So let's take a look at it here to see if you're on the right track and moving through it correctly. All right, so we have multiple steps here on this titration. And again, like I said before, when you have problems like this, typically speaking, you want to think of each problem as sort of like a separate problem that you started at the very beginning of titration and stopped at that point along the way. So we are titrating 100 milliliters of nitrous acid with 0.1 molar sodium hydroxide. So the setup of this is our sodium hydroxide right up in the burette. Down here we have our nitrous acid, and we're adding our sodium hydroxide to our nitrous acid. We have a Ka value for nitrous acid, so that immediately tells us this is a weak acid, right? And sodium hydroxide is a strong base. So we are doing the titration that we talked about in this example of the weak acid and strong base titration. That should give us a curve of, it kind of looks something like that going through it. So again, we have sort of our parts to our titration here. We're going to start with A, which is the initial solution. So that would be, pretty much, this spot right there. And at that spot, at the initial solution, really the titration has not begun yet. So we haven't added any sodium hydroxide. So really the only thing we have there is what's in the beaker, which is our weak acid. So as we talked about at this point in the titration, we are looking really at just a weak acid problem of nitrous acid. And it has a concentration of 0.1 molar and 4.5 to the -4 as our Ka. So we could go right into just a Ka problem here. So our weak acid is going to dissociate into H plus and nitrite here. That's going to give us a Ka of our products over our reactants. That's going to equal 4.5 times 10 to the -4. We again could use the molarity that was given to us because we have not added any base in this case, so we don't need to do moles here. So 0 and 0. Change going to be -x, +x, and +x. That means at equilibrium here, we will have 0.1 -x, x, and x. Questions so far? Hopefully this is what you were doing. And at this point, we're going to go into our expression. That will give us x squared. 0.1 minus x is equal to 4.5 times 10 to the -4. Now it is a small value of k, so we can assume x is equal to 0. I hope you checked it because it's not so good. I think it's about 6 or so percent if you tried the assumption and then checked it. So it's actually one where it's not a good assumption. So because of that, we cannot do that. We do have to basically do the quadratic on this opening one here. So we do need to multiply that to the other side. And if we do that, we will get x squared is equal to, let's see, 4.5 to the -4 times 0.1, 0.000045. And that's going to be -4.5 times 10 to the -4x, bringing everybody to the same side here. X squared plus 4.5 times 10 to the -4x minus 0.000045 equals 0. That's going to give us our A, B, and C for our quadratic. And in this case here, popping that in there, that's going to give us x is equal to -4.5 times 10 to the -4 plus or minus. If you do everything inside the square root, so you take b squared -4 times a, which is 1, times c, which is -0.000045. I believe inside the square root, you get something like 0.001802. If you then square root that, I believe you will end up with 0.0134. That will all be divided by 2 times a, which is 2 in this case. That again, like normal, is going to give us two x values. So doing the plus first, -4.5 to the -4 plus 0.0134. Guess it would help I punched the right number in there. Try that. There we go. And divided by 2, going to get us an x value of 0.006475. We will also do the subtraction there. So -4.5 to the -4 minus 0.0134 divided by 2. That is going to give us a negative -0.006925. Obviously, here we're interested in the pH, and we can see that it does equal x. So clearly here, our negative is not going to be a good choice. That would mean that our H plus concentration, which equals X, would equal our first X value we got there, 0.006475. That then could go into our pH minus the log of that. And that looks like we will end up with about a 2.19 as our opening pH here for our acid. It is starting with an acid and it is an acidic pH, so that is good, I think. Yeah. Any questions on any of those steps there? Yeah. So again, just a subtle reminder, make sure you do check it, yeah, and just don't roll with the assumption, yeah. All right, so we're building out there at like 2.19. We're then going to start this titration, right? And we want to know what is the pH after we add 80 milliliters of our base. So clearly at this point, we are doing the titration and we have added volume. So we should know, for example, that we need an ice table and we do need it in moles. So we'll do 80 milliliters of our 0.1 molar sodium hydroxide to our 100 milliliters here of our 0.1 molar nitrous acid. And that Ka is still the same one, 4.5 times 10 to the minus 4, I believe. All right, so I'm going to start with some moles here. So I'm going to go for my sodium hydroxide here. Again, converting my volume into liters, dividing by 1,000 or moving my decimal place over. Going to multiply it by the molarity, which is our moles per liter. That's going to get us 0.08 times 0.1. You get us 0.008 moles of sodium hydroxide. We'll do it for our nitrous acid, which is 0.1 liters, which is 100 milliliters converted into liters, times our molarity here, moles per liter. That's going to get us here 0.1 times 0.1. 0.01 moles. We could do our reaction, which obviously is our acid here and our base. Going to do obviously an acid base reaction. And we will get some sodium nitrite and some water in this case. Using our moles here, we had 0.01 moles. We had 0.008 moles here. Again, that is what we're starting with. That is what we are adding in this case, and we have 0. Once again, by just looking at our initial moles of what we started with and what we're adding, we see that the moles of what we're adding is less than what we started with. So that again should tell you you are before the equivalence point. Again, by knowing that you are before the equivalence point in this type of titration, you should also know you should end up with a buffer. So let's see if that is the case here. Change is going to be our base minus 0.008 moles, minus 0.008 moles, and plus 0.008 moles. That is going to get us at equilibrium here, 0.01 minus 0.008, 0.002 moles, 0 and 0.008 moles. We do need total volume at this point. We started with 100 milliliters of our acid. We added 80 milliliters of our base to it. That's 180 milliliters total volume. Converted to liters, 0.18 liters and 0.18 liters. Going to give us the molarity of what's left over, and we will end up with 0.0111. And on the other side there, 0.0444. Again, if you didn't recognize where you were at to begin with, you could still at this point look at your ice table. And once again, you should see, as we expected, these two guys are left over, the HNO2 and the sodium nitrite, which is again a weak acid and its conjugate base. And again, we do hit the buffer that we do expect in this type of titration. Because it is a buffer, we will go into our Henderson-Hasselbalch equation, which is the appropriate place to use it. We will need the pKa value, which is minus the log of the Ka, and that is minus the log of 4.5 times 10 to the minus 4. That's going to get us here 3.35 as our pKa value. So our pH would be 3.35 plus the log. Once again, the less hydrogens are the guy with the spectator ion, like a sodium, is our base. So that's going to go up on top. And our acid will go on the bottom. And that's going to get us here 0.0444 divided by 0.0111. And a little log action plus a 3.35. And that's going to get us at this point in the titration a pH of 3.95. Any questions on any of the parts there? Once again, as we talked about many times, you could skip the Henderson-Hasselbalch and ice table that again instead. And again, in this case, you probably would want to do HNO2 as a Ka problem, making sure you have the concentration on both sides of the arrow. Any questions on that one there? So we are rolling through. We're now up to, something like, really bad draw though. There we go here. 3.34, right? Now we're going to hit part C, which is the equivalence point. And as I mentioned before, again, this is a type of problem where they actually don't tell you the volume to reach the equivalence point. So again, this is going to be something where you're going to have to kind of figure out what the volume is to reach the equivalence point. So you have that volume to do your titration calculation. So let's take a look at that one here, which is the equivalence point. And again, we have our 0.1 molar HNO2, and we have 100 milliliters of it. We also are obviously using 0.1 molar sodium hydroxide and our 4.5 times 10 to the minus 4 Ka value. So as I mentioned before, there are several different ways you can figure out the volume to reach the equivalence point. Again, as we saw in the previous step there, it is a one-to-one relationship between the acid and the base. So you can use M1V1 equals M2V2, and in this case, M2 would equal our 0.1 molar times our 100 divided by our 0.1 molar. Remember, since this is such like the dilution equation, you do not need to convert out of milliliters here. You can actually leave it in milliliters. It will just give you the answer in milliliters. Those are going to cancel, and it will tell us if I solve for V2, which is actually what I'm solving for. If I solve for V2 there, that we need 100 milliliters to reach there. So we do need 100 milliliters. The quicker way of knowing that is if it's a one-to-one relationship and you have the same molarity for your acid and base, you need the exact same volume to get there basically as what you started with. So again, you also should know the number of moles should be the same, so you can use the molarity at that point to get you there. So we know our HNO2 moles is going to be 0.1 liters times our 0.1 moles per liter. And that's going to give us our 0.01 moles. We also now know from our calculation there that we need 100 milliliters of our sodium hydroxide, which essentially is going to give us the same number of moles, which is exactly what we would expect at this point because we are at the equivalence point, right? So they should equal each other in terms of the number of moles. So if we do our ice table here, we will have our HNO2 plus our sodium hydroxide giving us our sodium nitrite and our water in this case. And again, initially here, 0.01 moles. We are at the equivalence point, so 0.01 moles for this. As I mentioned before, you could also have at this point use the molarity equation, the 0.1 molar, and now you know how many moles you should have had, so you can solve for the volume as well. And that should give you the same 100 milliliters or 0.1 liters in this case. You cannot choose the wrong thing at this point, so that's good. That's got to be that number there, 0.01 all the way across here. That means, again, as we would anticipate here at the equivalence point, we have none of what we started with left. We have here 0.1 moles. This, again, is the place where knowing the volume is important so that we could get our total volume, which is 100 milliliters of the acid and 100 milliliters of the base we added together to get us to our 200 milliliters. We will divide this by 0.2 liters, and that will give us, again, the correct molarity, not dividing by 0.1 liters, 0.05 molar. Once again, knowing that we're at the equivalence point even before we did this calculation, we should know that we should end up with a salt, which is what we did end up with. We should also know that part of that salt will go through hydrolysis. It is not the sodium part because that's neutral. It is the nitrite part that comes from this weak acid. And because it comes from the weak acid, that means the nitrite here will act as its conjugate base. And once again, that is what it's going to do when it goes through hydrolysis here. So we would expect our NO2 minus to react with water. And again, it's going to react as a base and accept the H plus. Obviously, logic tells us it doesn't have one to give, so it's got to accept in this case. So that's going to give us nitrous acid. And that is going to produce hydroxide. And as we talked about previously, we would expect now our pH to be basic at this point. And by the way, we also need a KB, right, because of that as well. So remember, this is the spot where we use our equilibrium concentration from above. And again, that's really the purpose of that ice table, is to get the concentration of our salt that's going through hydrolysis, 0.05 molar. These will be zeros. Change will be minus X, plus X, and plus X. That means at equilibrium here, 0.05 minus X, X, and X. Any questions so far? As we just talked about, this is definitely a KB situation. We obviously have the Ka given to us. So again, we're going to use Kw to get to the correct Ka value. So our, I do it up here. Our Kb will equal our Kw, which is 1 times 10 to the minus 14, divided by our Ka of 4.5 times 10 to the minus 4. And that's going to give us the Kb value that, again, we do need to use. A reminder that when you do see hydroxide on the right-hand side, Kb is what you should be using, H plus, H3O plus on the right-hand side, Ka. That's going to give us a Kb of about, we'll call it 2.2 times 10 to the minus 11 in this case. So putting in our values there into our Kb will give us x squared divided by 0.05 minus x equals 2.2 times 10 to the minus 11. Here we can assume x is equal to 0. That's going to give us x squared divided by 0.05 equals 2.2 times 10 to the minus 11. We're going to multiply and then square root. And that is going to give us our answer here for x. And if we do that, we're going to times that by 0.05 and take a little square root action. That's going to give us something with a lot of zeros. That's going to give us here an x. I can go right here so you can hopefully see it. 1.05 times 10 to the minus 6 in this case. We do want to check it, so we could divide it by 0.05 and times it by 100, and the check is good here. It's less than 0.1%, so it's very much good. That, though, we do need to remember at this point, if we go to our ice table, is not the H plus concentration, but it is the OH minus concentration. So that is going to give us our OH minus concentration. Let's go up here, get rid of some of that there. So because that does equal the OH minus concentration, we could get our POH first, which is minus the log of 1.05 times 10 to the minus 6. If I do that minus the log, I end up with like a 5.98. And for some reason, you thought that that was the pH. It should not make sense to you in this type of titration because the equivalence point in this type of titration should be basic, right? And again, we know that obviously from our hydrolysis reaction right here. So we do need to subtract 14. So we're going to do a little subtraction there, and that's going to give us an 8.02 pH, which is basic and makes sense based on where we are in this titration curve. Any questions on that one there? Yeah. All right. So crawling up our graph here, we're now heading, obviously, we made our big jump to our 8.03-ish. And now we are ready really to kind of make the turn here, if you will, and kind of finish it out with D, which is what is the pH after 105 milliliters have been added. Clearly, that is past the equivalence point, as we just calculated that the equivalence point was 100 milliliters. So we're now past the equivalence point. We're at the point where you're just randomly adding base to it. So here, 100, that's 105, I think, right? Yep, 105. We got 105 milliliters of sodium hydroxide added. And again, it's the same molarity, obviously, to our 100 milliliters of 0.1 molar nitrous acid. So again, here we need some moles. So we got the moles previously there as 0.01 moles of nitrous acid. We'll get our moles here of our base 0.105 liters times our 0.1 moles per liter here. And that's going to get us 0.0105 moles. So again, we're ready to do our ice table here, HNO2, sodium hydroxide, NaNO2, and some water here, right? And again, we started with this guy, we adding this one here. So using our initial moles, 0.01 moles and 0.0105 moles there and 0. Again, if you were just doing this problem as like a standalone problem, you didn't have the other parts of the question like we had, we again could look at our moles that we're starting with, and we can see now that we are actually adding more moles than what we started with. And this again should tell you you're after the equivalence point. So again, if it was maybe just a question by itself, that is how you can compare. Again, the starting moles to figure out where you're at. Change in this case, because we were past the equivalence point, will be the acid. It becomes kind of the limiting reagent in this case. And that's going to be the subtraction all the way across. That means at equilibrium here, we have none of the acid left over because we just used it all up. We will have a little bit of our base left over, 0.0005 moles, and we will have 0.01 moles here. Total volume at this point is our 100 milliliters we started with, 105 we added, so we're at 205 milliliters. So we can convert everybody back into molarity here, 0.205 liters, 0.205 liters. And that's going to get us here 0.00244 molar and 0.0488 molar. We are again after the equivalence point, and we again can see we do have two things left over as we talked about previously. We do have our salt and we do have our strong base. And once again, our salt's going to act as a base. But again, as we talked about at this point in the titration, its contribution is going to be obviously much less than our strong base. So we will go with the contribution of the strong base because as soon as that goes in there, it's going to produce hydroxide. That means that this, once again, is not the H plus concentration, but it is the OH minus concentration. So that will get us to our POH minus the log 0.00244. Going to get us a POH at 2.61. Once again, if you thought that was the pH, should not make sense to you because in this titration at this point, you're just dumping base in there. So you should be pretty basic right at this point, and you're at the top of the curve. So that should be pretty basic. So the pH here would be 14 minus 2.61er. And that seems more like a good pH here, 11.39, which is definitely basic and probably puts us at the top of our curve. Any questions on that part of the titration curve? And again, that puts us up here, 11 point whatever it was there, 3.4. I think we just got 3.9 as we go that way. So again, understanding the titration curve, understanding where you're at should tell you, for example, you should end up with a buffer, should do hydrolysis and that type of stuff. It's really, really important. Question on any of those three titration curves we talked about or how to calculate the pH along the way. You obviously need to be able to recognize the curves, what they look like. You need to be able to calculate the pH along the way. Any questions? All right, the very last thing of this chapter is something we've been touching upon all through, which is indicators. And we did it the other day when we did the lab. So just to officially finish it out here, as you know, indicators work over a specific pH range, and they are thought of as really like weak acids. There is a protonated form and a deprotonated form over here. So one where it has the H and one where it doesn't have the H. Really the ratio of kind of the protonated part of the indicator to the deprotonated part of the indicator will tell you sort of the color that you will see. If it's kind of greater than 10, that ratio, you'll see kind of the acidic color. If it's less than 10, you'll see more of the basic color. Here's a big list of different indicators. Obviously, you don't have to memorize the list of indicators or their pH range they work over. But as you can see here, crystal violet is kind of yellow and then becomes green and then blue, actually. And it works over a more acidic type of range. Here you can see methyl orange is red and then kind of goes to orange. And then our favorite one ever, right, which is phenolphthalein right there. Again, kind of colorless in that 8-ish range and then kind of turns pinkish, 9-ish to 10, super dark pink in that area of it as well. So what is the color of these indicators, before you even get there? Technically speaking, this would be like orange all the way up there. And, this would be kind of reddish all the way up there until you kind of hit it. And then it'll kind of stay that other color past it as well. So the idea of an indicator is one where we want to make sure that we pick an indicator where it will actually change color near the equivalence point. And we would not, for example, want to choose phenolphthalein for a titration where the equivalence point is acidic, right? Because that's not going to change color at all, right? It's just going to be colorless near the equivalence point. It will never change color until you hit a basic pH, right? Or it may actually go in this case from like, if you're doing a titration that's like a base with an acid, it may actually start pink and then go colorless, right? So it might not be the best choice for it. You might want to choose something maybe like crystal violet that's more acidic, or any of those other sort of acidic indicators. You could do just a calculation like we just did, right? Like we just did for the equivalence point in your titration. And you could find approximately in your titration what the pH should be when it changes color. You could actually go to a list like this and choose a more appropriate one, maybe. That might work really well. So you don't want to pick one where the change is going to occur before the equivalence point, because that's typically we use indicators to tell us to stop our titrations. So here's another table of some indicators and the pH range in which they work over. They do have different colors in acidic and basic. So one last question here. What indicator would be a good one for nitrous acid and KOH? Which indicators on this list might be appropriate to use in this titration? So take a moment or two and think of which ones would be good. Obviously, this is actually the titration we just did. Instead of sodium hydroxide, you're using potassium hydroxide, but it's really the same titration we just did in that example. And from that example, we know that is a weak acid, right? And this is a strong base. And once again, here we are adding the KOH to our acid. We know from our titration calculation and also the curve, it should look something like this, where the equivalence point should be basic. So that pretty much will take out all of those as they work basically in the acidic range. So those are going to change color way too early for us, right? And it's not going to help us know when to stop our titration. That leaves us this one, which does dip a little bit into the basic range. To be honest with you, if you take the example we did, it was like 8-ish. So that's probably also going to change well before 7.6. So that's probably not going to be a great choice. This one here, the Creosol Red, probably would be okay. Again, it may not be the best because it tops out at like 8.8. And that's, as you saw from our calculation, just for that specific titration, we're at 8.03. So we might actually see a color change a little too early, and we might be stopping a little bit too early. Phenolphthalein is a pretty good one as well in this case, because it does work between that range. So again, like I said before, the two possible options could be either those last two. Again, if you had a list of indicators available to you, you could do a theoretical calculation of the pH at your equivalence point and choose really which one you would think would be best. But out of the choice here, based on the problem, those last two would be our best bet probably for indicators. Any questions on that there? All right. I think they agree with me, I hope, That is chapter 14, believe